All right, now in this lesson, we're going to talk about the covariant derivative, or parallel transport actually, parallel transport of PQ rank tensors. And we'll be focusing on leaning on the CFREE notation to do this. Although, as you've already sort of seen from the previous lectures, the CFREE and the comp, you kind of work with them together, right? You almost always slide from one to the other to get these proofs down. So we want to do parallel transfer for PQ rank tensors. Notice that we've done this already for vectors, right? We've got this for a vector, or likewise, we could write this as d by ds of this operator ts s at s equals t, right? So these are the two parallel transport equations, but you'll notice they're both defined for vectors, right? A vector field. And of course we also have the comp notation, right? dy mu d tau plus gamma mu alpha beta gamma dot alpha y beta equals 0, right? So these are the three forms of parallel transport, but they're all defined for vectors. Vector, vector. You solve this equation, you get a auto-parallel vector field along the curve gamma. Likewise, same with these two are just alternative expressions of the same thing. And all of these things are ultimately the same. And that last lecture we did was sort of a very long analysis of this guy, which I think was worth doing. Although you really don't see this too much in the books. It's the book that I saw it in, that I studied it from, was a book by a guy named Straumann, Straumann. Let me see if I can remember the title. The title was General Relativity with Applications to Astrophysics. And pretty good. It's a pretty good book. It's one of the harder ones. It's up there with Wald and Chandrasekhar's book. Okay, so but still, it's all for vectors. So now we have to think about this in terms of tensors, just general tensors, because everything should be able to do a parallel transport, right? If I have some curve in my space-time, you know, with some parameterization tau, some curve gamma that takes, you know, each of these points onto the curve. At this point, you know, I've been showing a vector space, but I could have any tensor product space. I could have, you know, Q alpha beta gamma delta, right? And that's a tensor that would exist at this point t. And then over here, there's a tensor product space for Q alpha beta gamma delta. And this guy should be parallel to this guy in a similar idea that vectors are parallel. Now, the thing about vectors is we kind of understand, oh, we understand how it works in flat space-time because we kind of visualize vectors in flat space-time. So we kind of understand the idea that, okay, we can understand what a parallel vectors are. And with the notion of curve space with a connection, right, with a connection, then we understand, okay, all right, so the basis vectors of these parallel vectors are changing, and we kind of need a rule to penetrate for these vector spaces, these separate vector spaces, to somehow be linked together on this manifold and kind of make sense. So the idea of this happening for tensors of arbitrary rank, it's a little bit tougher. Now you could go and lean on the idea, well, first you could just accept it. You could accept the fact that we need to come up with a way of parallel transporting tensors, and tensors should be parallel, right? There should be a way of doing that. In flat space, you would say the same thing, right? If you had a tensor, you know, Q01, these are the components, Q02, Q03, if those were, say, and then Q 1, 1, I guess 1, 0. Say you listed all the components of Q out. In flat space, you might say, well, when you move from T to S, the components should stay the same. Q, 0, 1 should be the same. Those two should be equal, and Q, 0, 2, those should be equal. That would be like parallel transporting a vector in flat spacetime. You just keep the components the same. It's another way of saying that the connection, mu, nu, gamma, equals 0 everywhere in the spacetime. So it's easy enough to understand how you might use that components don't change rule for flat spacetime, but it's not so easy to understand how that might change for a spacetime that's curved or a spacetime where the metric connection is not equal to 0. But ultimately, the basic problem is, let me select this. Let me get rid of this stuff here. The basic idea still is that now you have a tensor product space, T, alpha, beta, I guess this would be partial alpha tensor product dx beta. And you have one of those tensor products. It's still a vector space, right? We all know that. T alpha beta partial alpha tensor product dx beta. We know we have it. These are maps, linear maps, bilinear maps in this case. And I should be able to pick a value, a particular tensor at T, and find its parallel transported version at S using just the same process. And I should have the same operator moving from S to T. This operator acting on a tensor should give me the parallel tensor at a different place. And this is different than an arbitrary tensor field. There needs to be, what I need is an equation to tell me what is the autoparallel tensor field given a tensor at one point and a curve and a spacetime with a connection. Boy, that's a disaster. And a spacetime with a connection. So I have a curve in the spacetime, I have a spacetime with a connection, I have an initial tensor at some point. I should be able to calculate the parallel tensors at every other point on the curve. And so now we can do that for vectors. Now we have to do that for tensors. By the way, when I mentioned that we could go with the idea that the components remain the same, that for example T0, 1 in this point in flat space would be T0, 1 over here, that's flat space in a Cartesian system where the connection is actually 0 everywhere, right? If I have a flat spacetime where the connection is not 0 everywhere, then I'm still going to have these components changing even in flat space. That needs to be clear. Flat space in the Cartesian system where the connection coefficients vanish everywhere, then literally the components should in principle just move from one point to another, regardless of the path, in fact. But if you have flat space without, but you do have a connection that's non-zero, then the components will change as you move parallel transport from place to place. Okay, and the other thing is that there is a visualization you could lean on for one-forms, right? If you go back to our one-form lecture, and this isn't part of the prerequisites, but if you go back to the What is a Tensor series, and you considered the cotangent space, T star S of S, and then say T star of T on S. And so now we're talking about the space of all one forms, or just covectors. So every covector would look like A mu D x mu. You could imagine, we have a way of visualizing those things as these densities of these plane densities, right? Basically a one form has this appearance of a bunch of stacks. We called it a stack, and the density of that stack was relevant. So you could kind of imagine parallel transporting those stacks, right? And you know that whatever the curvature of the manifold, that is going to somehow play in making the stacks here parallel to the stacks here. And this curvature is going to make it so that it's not literally just the same direction. If you associate with the stacks a vector in the direction of the stacks, which is really not a good way of looking at it, because we're trying to get away from the arrows when we think about these stacks. But the stacks are going off in a direction, there's no doubt about that, and they have a certain density. So that's another visualization that could work for, if you've gotten good with this stack visualization of one forms, then you could use that to kind of bootstrap the logic that you would have of parallel transporting vectors, which we're pretty comfortable with. Okay, but we still got to kind of attack this creature here. We've got to figure out how to parallel transport an arbitrary tensor. Even if you were good with these stacks, that's still only covectors and vectors that you're down with. We still have these things to figure out. Oh, and by the way, you don't need to stop at the stack visualization if you're really pushed on to the end of the what is a tensor series, and you can do any form at all. You could do two forms, and you're dealing with these honeycomb structures. You could do three forms, and you're dealing with these. Well, I guess the three forms is the network, or the cells, all the cells, the density of cells. So there is some room to play in the lower dimensions, right? If you stick to, say, 3 dimensions or 4 dimensions, or you stick to 2 forms, I guess is what it is, you can kind of imagine shifting those around parallel to each other. So there is a way of visualizing the notion of what is becoming parallel to what with some tensors, in particular the forms. But the point is we got to get away from visualizing things, right? That's not the point. If you stick to what you can actually visualize, you're never going to make it very far in this business. Okay, so now we're going to dive into that abstract idea of how to create parallelism for arbitrary rank tensors, and we're going to start with covectors. So with covectors, we are going to have to come up with some kind of foundation that's going to drive us all forward through this. The first, let me establish the notation. TS, and I'll say some covector alpha, where alpha is at S, the parameter value S. This guy is an element of the cotangent space of gamma T at S. So just as a reminder, this is an operator that's going to take some tensor. It's going to take any tensor, right? The ones we've been doing so far are vectors, but we're going to upgrade this thing so it can take any tensor. It acts on the right. In this case, it's taking a one form. That one form is a covector, and it's a covector field along a curve. So again, we're always dealing with some curve gamma that's parameterized by tau, and in this case, that value is tau equals S, and that point is gamma of S. That's what this point is in the manifold. And if you want to really push it, the coordinates of that point are going to be x0 gamma of S, comma x1 gamma of S, comma x2 gamma of S, comma x3 gamma of S, right? So that's, when you really break it down, that's the point in R4 that it's mapped to from the manifold. So this is the manifold S, and this is the point in R4 that is the coordinates of that spot. So we're referring to the vector, a vector located on this curve, on this curve here, at the parameter value tau equals S. And this thing is alpha of t, where this alpha is essentially this autoparallel field that is autoparallel along this line, and this operator takes the vector that's at S and turns it into the one that's at T. So you can say, how would we do this? We would say AT equals that. So this is just a review of the same notation. The big step here is that we're promoting this so it doesn't just act on vectors, it acts on any tensor, and in this case we're just throwing in a 0-1 rank tensor. It's already been demonstrated and used for a 1-0 rank tensor, so we've already done that. So we're going to do it for a 0-1 rank tensor. Okay, so with all that in mind, see, going through this, right, going through this whole thing, repeating it in your head, getting it straight each time, that's worth it. That's worth it. Especially when you pick up a new book, you're going to have to look at it and say, okay, what does all this notation actually mean? We got a curve, we got a parameter for the curve, we got a name of the curve. All that stuff you have to kind of work out each and every time. Well, let me put it this way. I have to work it out each and every time. Okay, so with that, what is our guiding principle? Well, our guiding principle is, well, what is a one-form? A one-form, alpha of S, it's something that eats a vector. So we'll say I'll put in some arbitrary vector at S, and it gives you a real number, right? We know that from our earliest days. So this is true for any one form and any vector where now X is an element of the tangent space of gamma S at S, right? So notice this is at gamma T, because although this is at S, this turns it into something at T. So this is an element of gamma T, but X is an element of gamma S. A and alpha of S, I guess I should put the S there, is an element of the cotangent space at gamma S on the manifold. So we know that this statement is true. The dual space mapping of alpha at S with some vector at S will be a real number. So the notion of parallel transport axiomatically is going to mean that we want this value, whatever this number is, we want that to be preserved. We want the dual space mapping to be preserved under parallel transport, which means that omega ts of alpha s, comma omega ts of xs has to equal alpha at s, x at s. Right? So what this is telling me is that I take a vector at S and I parallel transport it to T, and I take a covector at S and I parallel transport it to T. If I take the inner product of those two parallel transported objects, I better get the same number as I would have gotten had I just taken the inner product in the tangent space at S. And that is our fundamental assumption about what parallelism should mean. And it certainly makes sense in flat space-time with regular vectors, right? You know, I take a vector here and I take a vector here. I take a vector here and I take a covector here, right? That dual space mapping should, if I parallel transport it, right? That dual space mapping should give me the same answer. The number of planes pierced by this arrow should be the same if we truly parallel transported the stack along with the vector. I should be a little careful because the prerequisites for this course don't include the stack visualization of one forms that we did in What is a Tensor. So you either have to just accept this with or without the ability to visualize the stacks for one forms, but it's really not that critical. The principle is pretty straightforward. The dual space mapping should be preserved under parallel transport. Notice though that's not the same as saying the inner product has to be preserved, right? If I took the inner product of two vectors, xs and y at s, right? That's the inner product, right? So that would be G, the metric tensor, acting on x of s and y of s. If I really did it out the full way, I would say G alpha beta dx alpha tensor product dx beta acting on x alpha or x, not alpha, but x, I guess it would be x gamma, partial gamma, y, zeta, partial zeta, something like that. So this is the inner product, this is the metric tensor acting on a two vectors, both located, everything here located at the point S, right? This is at S and that's at S. So I guess that would be x gamma of S, partial gamma evaluated at S, right? That's what would go here. That demand, the demand that the inner product be the same under parallel transport, is totally different, right? Because this parallel transport is driven by the connection on the space-time, right? Which in the abstract notation is nabla, in the comp notation is alpha, beta, gamma, something like that, right? Two different notations, but that connection's a piece is a structure of the manifold itself. This metric tensor is some other structure. Now, the demand that the metric tensor's inner product of two vectors, or equivalently, if I wrote it in this form, tensor product partial beta, the inner product of two covectors, which I could put here and here, right? Two covectors, omega and say, delta, two covectors. Likewise, those inner products could also in principle be preserved under parallel transport. But if they were, it's a different requirement than the one I'm setting up. This requirement here is parallel transport preserves dual space mappings, and this one would say parallel transport preserves the inner product, and these are not the same requirements. However, what we're going to discover is that if we demand this, that's going to severely constrain our choices for the connection on the manifold. In other words, you can't have both, right? You can't arbitrarily choose a connection and then demand this, right? If you arbitrarily choose a connection, you probably won't get this. If you demand this, you're forced into a connection, and that's the trick. That's what we're headed for. We're trying to prove that, because we're going to demand this ultimately, and we're going to discover that it forces us to have that. It forces us to have a specific connection on the manifold, and that's where we're headed with all this. But for right now, we don't have any of this. Right? We have no demand that the metric or that the inner product of vectors or covectors be preserved under parallel transport. We're only demanding that the dual space mapping be preserved. Okay. So now how would this demand look for full-blown tensors, right? We just showed it for dual vectors, but I could write, imagine I had a tensor at the point S. Now this is a tensor of any rank, right? So in the comp notation, this thing would be like I1, I2, to IP, and then Q1, Q2, to, whoops, I guess Q is not a good choice. J1, J2, to JQ. And then that would be a PQ rank tensor, right? That's what the component would look like. And then in the component form, this thing would be partial I1, tensor product, partial IP, tensor product D, X, J1, D, X, JQ, like that. And it's a mapping, right? So we know that it's going to take what is it going to take? It's going to take Q covectors and I'm sorry. It's going to take P covectors and Q vectors as arguments. So we write all that down like this. We just write this, and then I'll go sigma 1 dot 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 sigma p, and then z1 dot 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 zq, right? And that is a real number, right? Because that's what these things are. So this is the abstract notation. This is sort of the comp notation. And when I say this is the comp notation, right, this is the full-on comp notation, including the basis vector, right? And as I keep pointing out in your textbooks, all you're going to see is this very, very often, because they don't usually drag around these basis vectors. But it's all implied because the way the indices are ordered, right? The ordering of the indices tells us how these basis vectors are arranged. So it's redundant notation. And that's the whole purpose of the What is a Tensor series, the first half of it at least. There is a textbook notation form, by the way, just be aware, where you would write QI1 IP, and then you would write J1 to JQ like that, right on top of each other, right? So the indices are right above each other. When you do that, you've got to think of it in terms of this, right? Usually the author will tell you what he thinks is coming first in the basis vectors. The point is that this is a shorthand, typographically compressed form of this, and I can appreciate why you might want to do it. You know, when I do a lot of stuff in LaTeX, this actually becomes pretty extended sometimes, and this is a lot tighter. But you know, strictly speaking, I don't like to deviate from this. This is a literally captures the entire structure of the tensor because you have the index ordering. Here you do have the index ordering, but you know, is the moment you would want to raise one of these indices, for example, one of the j's, or lower one of the i's, you immediately have to go back to this anyway. So, although admittedly you don't typically do that. Okay, so the point is we're going to work with this thing. So what does it mean to parallel transport this thing? Well, actually, so all right, so before I begin that, I have to make it clear that these guys are all at S, right? Right. This is a tensor field, and it's at S. And remember, we're still dealing with a curve. So when I say it's a tensor field, it's got to be defined at least along this curve. So that's Q of S, and it lives inside a tensor product space. I guess that would be T P Q of S. That's the tensor product space. And then these guys live in the tangent space of S, or the cotangent space of S, and these guys here, the vectors, live in the tangent space at S. Now, I've already kind of slipped, right? This has got to be T star gamma of S, because this subscript on these spaces should be a point in the manifold, right? And remember, S is not a point literally in the manifold. S is a value of some parameter that gets mapped to the curve through gamma onto the manifold. So actually the parameter is tau, right? And when the parameter is tau and S is a value of tau, right? So I'm kind of using this shorthand again, and it happens a lot in this field, right? You've got to keep track of what this shorthand means, so I repeat it each time it happens, or each time I notice that I'm doing it. Okay, so these guys here are all in the cotangent space at S. These guys here are all in the tangent space at S. And this guy here is from the tensor product space at S. Okay, so what does it mean to parallel transport a tensor? So what it means is the following simple principle. This guy's allowed to parallel transport things from S to T, right? So the parallel transport, so Q has to start at S. So this object is the parallel transport of Q, and we're going to call that Q of T. So this is, this is perpetual grounds for confusion between tensor fields and autoparallel tensors. I'm saying that I have a tensor in the tensor product space at the point identified by S, and I parallel transport that. And this is what I'm going to call that parallel version of Q. So Q is an autoparallel tensor field, right? It's a field where each value of Q at every point along this curve is parallel to the other value. Now, typically when we've talked about, if I write Q of X, I'm talking about a tensor field on the manifold where this tensor field has some value at every point X. And it can be an arbitrary tensor field that I'm talking about. And such a field is not typically autoparallel, right? It's just a tensor field. This notation looks very similar to this. And indeed, we are talking about Q as a tensor field, but we're talking about Q that's constructed specifically to be autoparallel for the purposes of this demonstration. So, we could abandon this and just say that this is the autoparallel version of Q of S at T. And that would be our symbol. And that's probably the safer way to go. But the key is this. The autoparallel, or the parallel of Q of S, that's going to be a tensor at T. And it's going to operate on a bunch of objects at T. So it's going to operate on psi 1 at T, on our sigma P at T, and then, I guess what was I using, Z? Z 1 at T to Z Q at T, right? So this is now a tensor at T that's autoparallel, or that's parallel to QS, and these are a bunch of covectors and vectors at T, and this guy here is going to be a real number, right? So that has to equal the following thing. That has to equal the original tensor field at S operating on the inverse of this motion, right? The inverse of this motion, where each of these guys is parallel transported to S, right? So TS, and then inverse TS Z1 T dot 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 TS ZQ of T. Right? This relationship has to hold. And that's very, very similar to this relationship here. In fact, it's for one forms, the idea that if you go back to one forms and you write down Ts of alpha starting at S acting on omega Ts of X starting on S, that has to equal alpha at S, X at S. You could also interpret that as omega Ts acting on alpha of S times X acting on T equals alpha of S Ts inverse X on T, like that. And this second one is essentially, this expression of the second one is going to be, I'm running out of room, so I'll write it, I'll lead your eye in red, and I'll write it up here. It's essentially omega Ts alpha of S, which is a covector at T operating on X of T, right? Which is this expression which is this expression with P equals 0 and Q equals 1. And then this side is essentially this expression, same, P equals 0, Q equals 1, right? So that has to equal alpha of S acting on t as inverse x of t. Right, so this expression says I start with a vector x at t, and I parallel transport it back to S. Notice this operator is an operator that takes vectors from S and brings it to T, so the inverse takes it from T to S. I could just switch the S and the T, by the way, but I like to keep the inverse in this circumstance. So now this guy is a vector at S, and I operate it with alpha at S. That should be the same number as if I take alpha at S, parallel transport it to T, and then operate on this thing that never moved at T. Right? So this is what we've already done is the p equals 0, q equals 1 version of the general case. Okay, now to get further we need to clean up a little bit. So clean up meaning we're going to sort of simplify our notation a little bit. So here's our curve, here's our parameter tau. What I'm going to say is that when tau equals 0, we are dealing with the point we're going to call P. So gamma of 0 equals the point P in the manifold. And then I'm going to say that if we were to go to another point in the manifold parameterized by S, right, if I want to do parallel transport from 0 to S, I'm now going to just write omega S. That's always going to be understood as omega from 0 to S, right? Like that. So I'm basically fixing, I'm taking my omega S to T, right? And first of all, I'm changing it up. I'm calling it, say, T to S, and then I'm fixing T to be 0, so I'm saying this is always going to be that, and then I'm saying since it's always going to be 0, I'm just going to write it like that, right? So this is always going to be interpreted as from 0 to S. And so omega S inverse can be interpreted as omega from S to 0. And where S can be any parameter value of tau. All right, so omega S is the parallel transport from 0 to S, and omega inverse S equals omega S to 0. And now I'm going to lean on my notion of what I expect for the parallel transport equation, right? The parallel transport equation is going to be something like this. I would normally write the connection, the curves, the derivative of the curve, right? And the tensor that we're taking the parallel transporting, that normally equals 0. And I'm going to say, well, I'm going to use this operator form, d by ds, evaluated at s equals 0, right? Because that would have been s equals t in our previous notation. The inverse function of s, meaning moving from s to 0, right? I'm moving from s to 0 based on this notation here is from s to 0 of q at gamma, evaluated at gamma s. That equals 0. And this is, so both of these are defining equations for parallel transport of q. And we're going to show that this basically satisfies all of the demands that we had made over here with this stuff, with these expressions about parallel transporting the arguments or parallel transporting the tensor. Now another thing we always have to keep in mind is that for 0,0 tensors, this guy here equals this vector acting on f, right? Remember that rule always exists for when f is a 0,0 tensor or a function on the spacetime. the covariant derivative in the direction of the curve is the tangent vector to the curve acting on the function. Right? That's just a flat-out rule that we talked about a couple lessons ago. That is just understood to all. That's the only way it could work, right? There's functions functions that aren't just flat-out functions that are 0, 0 tensor. They don't respond to the connection on the manifold. Okay, so now with that we need to demonstrate a few key things before we can proceed. Some algebraic kind of things, because what we're going to do is with that notation, right? We're going to go with this, right, on sigma 1 of 0, sigma p 0, z1 0, zq 0, right? That has to equal q of s inverse s sigma 1 0 dot 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 inverse sigma p 0 comma inverse s z1 0 inverse s zq of 0. Right, that's the expression. We're using this sort of abbreviated notation for the omega operator. So now consider this expression just for one particular tensor. Let's say that q of s is, let's see, I'm using z as my sort of argument tensor, so I need, let's say it's x of s, inner product, and then I'll say alpha at s, right? So that's a rank 1, 1 rank tensor. So I'm just constructing an arbitrary 1, 1 rank tensor, and I'm kind of breaking it into its vector piece and its covector piece, right? So so that's q. So if I write omega s of q of s, what I'm really writing is omega s of x at s, tensor product alpha at s, right? And so what this is telling me is that I'm taking a vector at s, and I'm taking a tensor at s, and I'm moving it to 0, right? That's what, 0, 2s. Wait a minute, this is 0, 2s. So I would need to start with, hold on. Okay, hold on. See, the notation is even, look, this stuff's confusing, don't get me wrong, I kind of screwed this up myself, but clearly you can see this makes no sense. This takes it from 0 to s, right, using our prescription here, right, from 0 to s, that's what that thing does. So this thing has to start at 0, right? So that's got to be 0. Likewise, this definition here, these guys have to be starting at 0, right? Okay, so given that, you can imagine feeding this thing, which is now a tensor living at s, you want to feed it one covector at s, and I'll call the vector at s z, right? That's what I've been using, I think. So if we do this, according to our definition of parallel transport, right, that's going to be x0 tensor product alpha 0 acting on s inverse sigma s omega inverse z s, like this. But this we can calculate, right? We can calculate that. That's going to equal omega s inverse sigma s acting on x0 multiplied by the dual space map of alpha of 0 omega inverse s z s. Right? So once we have that expression, we can compare it with omega s of x0 tensor product, right? So remember this thing here, that's a vector located at S, tensor product with omega s at alpha 0, and that is a covector. And if we fed that sigma at 0 and x at 0, right? So this is a vector at S, and this is a vector at S. So I need to feed it two vectors, a covector and a vector at S, right? At S and at S. And that thing is going to equal sigma at S, comma Sx of x0 multiplied by sigma, multiplied by omega s of alpha at 0 x at s, like this. And so now we compare this product with this product. But we've already know how this works for covectors. We've demonstrated it before. Back, where did we do this demonstration? Right here, right there. We're demanding this parallel transport doesn't affect this inner product, and I think I wrote it down here also, right? That this parallel transport, no matter how you do the parallel transport, whether you transport the vector to where the covector is and do it, whether you transport the covector to where the vector is and do it, do the dual space mapping, or you take a vector and covector at one place and transport them both to a new place and do it, doesn't really matter. It's all going to be equal. And so when you look at this and you compare this expression here is got to equal that expression there, because this one is just taking the covector and parallel transporting it to where the vector is and taking the dual space map, and this is taking the vector and parallel transporting it to where the covector is. So this product equals that product, and likewise that product equals that product. And the point of that is that this operation is equal to this operation, and the lesson there is, I guess I should just rewrite it, is that the parallel transport of a tensor equals the tensor of the parallel transported components of the tensor, or pieces of the tensor. In other words, this operator commutes with the tensor product. That's another way of saying it kind of formally. Now you can take this is important fact, right? That's the algebraic fact. And remember, so we're dealing with CFREE notation, right? So in CFREE notation, we can't lean on the rules of multiplying real numbers like the components of tensors are functions on the space-time, right? And we can multiply these things together using our regular algebraic rules. We kind of have to prove every algebraic rule from scratch. So we need to show that this operator, this parallel transport operator, commutes with the tensor product. And to do that, we used our basic principle that, and that proof, we didn't have to drop to, we did no comp notation here, we did no component notation here, but we did have to go back to our presumption that parallel transport preserves inner products, and that's how we said that this statement here was equal to that, this parallel transport preserves dual space mappings, not necessarily inner products, dual space mappings. So this dual space mapping is equal to that dual space mapping, this one is equal to that one, therefore this expression is equal to this expression, which allows us to write this down and say that parallel transport commutes with the tensor product operator. Okay, now that we've shown that, let's demonstrate that the partial derivative in the direction of the vector x of tensor q with respect to, tensor q with the tensor over the tensor product, all at a point P, right? Let's show that this obeys the Leibniz rule, right? Let's show that this guy operates on this product in a Leibnizian fashion, right? Let's make that's an important thing to know. And it's true, and we'll have to use our abstract definitions to show it. Now, why not tighten up the notation again? Just because it's done so many different ways. Here what I'm saying is I'm picking a vector x, q, and t. Obviously, it's all these things have to be associated with, this has to be some kind of tensor field, right? Because we're taking the covariant derivative of a tensor field. Ultimately, we have to understand what that means. We've already done we're working on parallel transport of a tensor field, but we can already show some facts about this right now, which we will do. But it's happening at a point P, right? Now, a point P is an element of the manifold, and that element has got to be nailed down to a, say, a parameter value s, because it's on a curve gamma. So we always have this curve, we always have tau, we always have a point s, we always have gamma s, and that gives us a point we're going to call P, which is in the manifold. So I can now express Q and S in different ways, of course. I can say Q at the point P. I can say Q at the point gamma S. Or I can write this as just Q of S, which is what I did in the last set of slides. Or I could write this as, say I could put Q of P, a subscript P there, right? And if in the last set, there was a point where we were dealing with Q0, so I would write Q0, could be Q gamma of 0, could be Q sub 0. Yeah, that's right, this could also have been QS, right? I could have done that. And this could have also been Q, the name of the point gamma 0. So if gamma 0 equals, say it was P, I could make it QP. So we can work with this sort of notation also, where we use this sort of subscript. Now the problem, of course, is when you go to comp notation, you're going to have QS, the mu component of QS, right? This becomes the name of something, and that subscript is not a space-time index, and you're now having space-time indexes mixed with named indexes, and it's really not that much of a mess in LaTeX, because this Q would be boldface, and the S would be a different script or a different type of font or whatever. So it's not that big a problem in modern production at all. And any of these things will really work okay. The one I don't like the most is this one, just because it gets so horizontally bulky. But at the same time, it tells you everything. It gives you the name of the curve. It gives you the value of the parameter. Because it's in the argument, it reminds you that Q is on this manifold. I mean, all that stuff should be at the forefront of your mind anyway. But, if you really had to revert to everything back to its basics, then this is probably where you would end up, and just have big, heavy formulas with all the details. When you do that, by the way, be careful to alternate your, especially if you do any LaTeX work, be careful to alternate stuff, parentheses with brackets. I would actually write this as Q bracket gamma parenthesis S, like that. You don't want to deal with this kind of situation, right? You'd much rather deal with this, than braces. And hopefully you don't have to go much farther than braces. But I would definitely go parentheses, brackets, braces when you handle this stuff. Okay, but enough of the diversion. Let's get back to the proof. So the proof, right? So this one is actually pretty easy, right? We write any tensor, Q, tensor product, S, operating at P. By definition, that's going to be D. This is why we went to all the lengths to prove that other thing. This fact, make it inverse S inverse. And then I'm going to use my new slick notation. Right? So this is the definition, right? We're talking about the covariant derivative of a tensor product of two tensors, right? And this is our old definition that we did in the last lesson. This takes us from 0 to S. So now we're going from S to 0. The inverse takes us from S to 0. And these guys are a tensor Q at S and a tensor S at parameter value S. So here, in this example, the curve gamma is not referenced at all, right? It's only referenced through its parameter. Actually, it's what's interesting is the parameter of gamma is tau, and S is a value of tau. So we've actually lost all reference to the actual curve itself, except perhaps this X, which is presumably tangent to that curve, right? That X is we're presumably doing this derivative, this vector here that lies in the directional part of the covariant derivative, that's tangent to some curve that you're in principle dragging these points together along. All right, so the curve is pretty much gone. I suppose the only way to really get it back here would be to do this, gamma dot. And that's fair, we could do that. But for the reason that we don't need to is you don't really need to think of a curve too much here, because X is tangent to some curve. The very definition of X being a vector, right, in the tangent space at the point P is that there's some curve out there where X is tangent to it. That's what it means. That's the very definition of vectors in a tangent space. So we always know there's some curve out there that'll suffice for this, and it doesn't really matter which one you choose. There's actually a lot of curves that have X as the tangent vector, and any one of those curves will suffice for the calculation of the derivative. You don't really need to know, because everything's done in limits, and with these limits, the effect of the way these curves differ away from the point P becomes less and less relevant. In fact, it limits to not being relevant at all. Okay, so this is our expression, right? Now what we just proved a moment ago is that this is going to be the same as this, right? This is the same as this. That's why we proved that last statement, is because we knew we would need it for this. And now we're dealing with an ordinary derivative, right? Here we're wondering what's the behavior of this covariant derivative in the direction of X vis-a-vis the tensor product operator. But this is a regular derivative, and we know that that's Leibniz. So we now write this down as d ds, evaluated at s equals 0, of S inverse QS, tensor product. Now this, I guess, I'll put in braces. Tensor product, well, I don't need a brace there. I'm still at the bracket level, right? SS plus D ds at S equals 0. Oops. Sorry, erase that. Inverse SQS tensor product brace DSS equals 0 of S inverse S at S, like this, right? And And we're done, because this is the definition of the covariant derivative of Q of S, and along this curve, right? And the curve comes in here because S is parameterizing the curve of which the vector x is a tangent vector. And this here is the covariant derivative of S. So that means that this whole thing is f of x q and times, hold on. Oh yeah. I got to remember, this is done at s equals 0. It's done, s equals 0 applies to the whole thing, right? So I have to write s equals 0 to that and s equals 0 to that. And then, so that's tensor product s plus q tensor product s, like this, where this whole thing is now at s equals 0, which of course means all of these guys are at p, which is what we were after, right? Getting it all at p. So this shows that the covariant derivative in the direction of some tangent vector x is Leibniz with respect to the tensor product. So we've got the fact that it's Leibniz with respect to the tensor product, and in order to prove that, we use the fact that the operator, the parallel transport operator, commutes with the tensor product. And this has all been in CFREE notation so far, right? So everything, we haven't dove into comp notation at all. So in this lesson, we covered the following points. We defined, using the operator form of this notation, we defined the parallel transport equation in an operator CFREE form of an arbitrary tensor Q. And we showed that the parallel transport operator sort of commutes with the tensor product operator. We showed that the covariant derivative in the direction of x is Leibniz with respect to the tensor product operation, which is a way of saying that this operator, this covariant derivative in the direction of x operator, is a derivation. It's a derivation in the tensor algebra. That's the word it uses. If you're Leibniz, you're a derivation, they say. You could be an anti-derivation, which would have an extra term over here. And anti-derivations are big deals in the study of forms. But this is just a straight-up derivation, and it's essentially the Leibniz rule, where the product is the tensor product. Then this is our definition of how to parallel transport a tensor. We say that a tensor parallel transported from one point to another, a distance s away along a curve, acts on a bunch of vectors and covectors at that new point. It's the same as leaving the tensor alone and taking all those vectors and covectors and shifting them in parallel form, parallel transport, back to the location of the tensor. You better get the same value. And taken to its simple conclusion for a 0, 1 tensor, you can derive the dual space mapping of a vector and a covector at a point is the same as the parallel transported covector and vector at a different point. Likewise, you could parallel transport one to the other or the other back to the first, and all of these numbers will be the same. Okay, so now we have to prove something about contractions, and once we've done that, we'll start being able to do some conversion into comp notation, and we're getting closer and closer to our ability to define the metric connection, where this idea of the preservation of the dual space mapping is converted to the preservation of inner products. And once we do that, we're going to bind the connection with the metric. And that's our goal.